Hello and what's up? Good morning everyone. My name is Francis Flaga. I am grade 11, section Jacamos. This morning I will share with you the definition of terms and example of a domain, friend, set, function, and relation. I hope you like my video. Okay, let's start. Welcome back again mga kamag-aral ko. Ako nga pala si Neil Francis Flaga. Sa pagpapatuloy po ng ating video presentation, huwag niyo akong kalimutan i-share and like ang ating video.
Let's have a little bit of a review of what a function is before we talk about what it means, what the domain of a function means. So a function we can view as something, so I'll put a function in this box here, and it takes inputs, and for a given input, it's going to produce an output, which we call f of x. So for example, let's say that we have the function, f of x is equal to 2 over x. So in this case, let me see, so if that's my function f, if I were to input the number 3, well, f of 3 that we're going to output, we know how to figure that out. We've defined it right over here. It's going to be equal to 2 over 3. It's going to be equal to 2 over 3. So for that input, we were able to find an output. If our input was pi, then we input into our function, and then f of pi, when x is pi, we're going to output f of pi, which is equal to 2 over pi. So we can write this as 2 over pi. So we were able to find the output pretty easily. But now let's do something interesting. Let's attempt to input 0 into the function. If we input 0, does the function tell us what we need to output? Does this definition tell us what we need to output? So if I attempt to put x equals 0, then this definition would say f of 0 would be 2 over 0, but 2 over 0 is undefined. Let me write this, 2 over 0. This is undefined. This function definition does not tell us what to actually do with 0. It gives us an undefined answer. So this function is not defined here. It gives a question mark. So this gets to the essence of what domain is. Domain is the set of all inputs over which the function is defined. So the domain of this function f would be all real numbers except for x equals 0. So let me write down these big ideas. This is the domain. The domain of a function. Actually, let me write that out. Domain of a function. The domain of a function is the set of all inputs over which the function is defined. Over which the function is defined, or the function has defined outputs, over which the function has defined outputs. So the domain for this f in particular, so the domain for this one, if I wanted to say its domain, I could say, look, it's going to be the set, and this curly brackets, these are kind of typical mathy set notation. I can say, okay, it's going to be the set of, and I'm going to put curly brackets like that. Well, x can be a member, this little symbol means a member of the real numbers, but it can't just be any real number. It can be most of the real numbers, except it cannot be 0, because we don't know this definition, it's undefined when you input a 0. So x is a member of the real numbers, and when we write real numbers, we write it with this kind of double stroke right over here. That's the set of all real numbers, such that we have to put the exception. X equals 0 is not a member of that domain, such that x does not equal 0. Now let's make this a little bit more concrete by doing some more examples. The more examples we do, hopefully the clearer this will become. So let's say we have another function. And just to be clear, we don't always have to use f's and x's. We could say, let's say we have g of y is equal to the square root of y minus 6. So what's the domain here? What is the set of all inputs over which this function g is defined? So here we are inputting a y into function g, and we're going to output g of y. Well, it's going to be defined as long as whatever we have under the radical right over here is non-negative. If this becomes negative, our traditional principal root operator here is not defined. We need something that, if this ended up being a negative number, hey, well, how do you take the principal root of a negative number? We're just saying this is kind of the traditional principal root operator. So y minus 6 needs to be greater than or equal to 0 in order for g to be defined for that input y. Or you could say, add 6 to both sides, y needs to be greater than or equal to 6. Or you could say g is defined for any inputs y that are greater than or equal to 6. So we could say the domain is a set of all y's that are a member of the real numbers such that they're also greater than or equal to 6. So hopefully this is starting to make some sense. And we're always used to functions defined this way, but you can even see functions that are defined in fairly exotic ways. You can see a function, say h of x. H of x could be defined as, it literally could be defined as, well, h of x is going to be 1 if x is equal to pi, and it's equal to 0 if x is equal to 3. Now what's the domain here? And I encourage you to pause the video and think about it. Well, this function is actually only defined for two inputs. We know h of pi. If you input pi into it, we know you're going to output 1. And we know that if you input 3 into it, h of 3, when x equals 3, you're going to put some commas here. You're going to get a 0. But if you input anything else, what's h of 4 going to be? Well, it hasn't defined it. It's undefined. What's h of negative 1 going to be? It hasn't defined it. So the domain here, the domain of h is literally, it's just literally going to be the two valid inputs that x can be are 3 and pi. 3 and pi. These are the only valid inputs. These are the only two numbers over which this function is actually defined. So this hopefully starts to give you a flavor of why we care about domains. Not all functions are defined over all real numbers. Some are defined for only a small subset of real numbers, or for some other thing, or only whole numbers, or natural numbers, or positive numbers, or negative numbers, or they have exceptions. So we'll see that as we do more and more examples.
In a set of data arranged from smallest value to largest value, range is the difference between the greatest and smallest value. Range is the statistical measure of dispersion, highlighting how different the numbers are. For example, if you read a book Monday through Friday and wrote down how many pages you read each day, you could take the range. To find the range, you put the number of pages in order from least to greatest. In this case, you would have 3, 8, 9, 11, and 12.
Gets kick.
Now, you subtract the smallest value from the greatest value to get the range. R equals 12 minus 3, which equals 9. The range of this data set is 9 pages. Here are the 3 steps you have to do to calculate the range of any data set. 1. Gather your data, so you know all the numbers to be studied. 2. Arrange the data set in order from least to greatest. 3. Write a subtraction sentence to subtract the smallest value from the greatest value. Let's try this with a set of real numbers. We will start with easy numbers. Here are 5 of the lowest scoring games in NBA history, listed with teams and total game points. Washington Capitals 49 versus Pittsburgh Ironmen 40, 89 points. Fort Wayne Pistons 19 versus Minneapolis Lakers 18, 37 points. Washington Capitals 50 versus Detroit Falcons 33, 83 points. Boston Celtics 46 versus Pittsburgh Ironmen 44, 90 points. Boston Celtics 47 versus Washington Capitals 38, 85 points. Now let's go through the 3 steps to find the range in the total points scored per game. Step 1. Gather your data. We have 5 total data points to study. 89 points, 37 points, 83 points, 90 points, and 85 points. Step 2. Arrange the data set in order from least to greatest. Finally, Step 3. Write a subtraction sentence to subtract the smallest value from the greatest value. That will be R equals 90 points minus 37 points, which is 53 points. The range of the 5 lowest scoring games in NBA history is 53 points. Let's try this with some more challenging numbers, like country populations. China has an estimated population of 1,420,062,022 people. Mexico's population is 132,328,035. India has a population of 1,368,738,513. The United States has a population of 329,093,110. What is the range of this data set? Here is the data that we needed to gather. Next, we arrange the data set in order from least to greatest. And now we subtract the smallest value from the greatest value. This gives us our range. The range of populations in these 4 countries is 1,287,733,987 people.
So in a relation, you have a set of numbers that you can kind of view as the input into the relation. We call that the domain. You could view them as the set of numbers over which that relation is defined. And then you have a set of numbers that can be, you could view it as the output of the relation, or what the numbers that can be associated with anything in domain. And we call that the range. And it's a fairly straightforward idea. So for example, let's say that the number 1 is in the domain, and that we associate the number 1 with the number 2 in the range. So in this type of notation, you would say that the relation has 1, 2, 1, 2 in its set of ordered pairs. These are 2 ways of saying the same thing. Now the relation can also say, hey, maybe if I have 2, maybe that is associated with 2 as well. So 2 is also associated with the number 2. And so notice, I'm just building a bunch of associations. I've visually drawn them over here. Here, I'm just doing them as ordered pairs. We could say that we have the number 3. 3 is in our domain. Our relation is defined for number 3. And 3 is associated with, let's say, negative 7. So this is 3 and negative 7. Now this type of relation right over here, where if you give me any member of the domain and I'm able to tell you exactly which member of the range is associated with it, this is also referred to as a function. And in a few seconds I'll show you what a relation that is not a function. Because over here you pick any member of the domain, and the function really is just a relation. It's really just an association, sometimes called a mapping, between members of the domain and particular members of the range. So you give me any member of the domain, I'll tell you exactly which member of the range it maps to. You give me 1, I say, hey, it definitely maps to 2. You give me 2, it definitely maps to 2 as well. You give me 3, it's definitely associated with negative 7 as well. So this relation is it's obviously a relation, but it is also a function. Now to show you a relation that is not a function, imagine something like this. So once again, I'll draw a domain over here. Then I do this big fuzzy cloud thing to show you that I'm not showing you all of the things in the domain. I'm just picking some examples. And let's say that this big fuzzy cloud looking thing is the range. And let's say in this relation, and I'll build it the same way that we built it over here. Let's say in this relation, 1 is associated with 2. So let's build a set of ordered pairs. So 1 is associated with 2. clear association. If I give you 1 here, you're like, I don't know, do I hand you a 2 and 4? That's not what a function does. A function says, if you give me 1, I know I'm giving you 2. You give me 2, I know I'm giving you 2. Now that only way was like, so let's think about it this way. Numbers that are associated with the numbers in the domain. The range includes 2, 4, 5, 2, 4, 5, 6, 6, and 8. 2, 4, 5, 6, and 8. I could have drawn this with a big, a cloud like this, and I could have done this with a cloud like this. But here we're showing the exact numbers in the domain of the range. And now let's draw the actual associations. So -3 is associated with 2, or it's mapped to 2. So -3 maps to 2 based on this ordered pair right over there. Then we have -2 is associated with 4. So -2 is associated with 4 based on this ordered pair right over there. So the first ordered pair, I don't want to get that confused. It should just be this ordered pair right over here. -3 is associated with 2. Then we have -2, there's the color. We have -2 is associated with 4. -2 is associated with 4. We have 0 is associated with 5. 0 is associated with 5, or sometimes people say it's mapped to 5. We have -2 is mapped to 6. Now this is interesting. -2 is already mapped to something, and it's now this ordered pair saying it's also mapped to 6. And then finally, I'll do this in a color that I haven't used yet, although I've used almost all of them. We have 3 is mapped to 8. 3 is mapped to 8. So the question here, is this a function? And for it to be a function, for any member of the domain, you have to know what it's going to map to. It can only map to one member of the range. So -3, if you put -3 as the input into the function, you know it's going to output 2. If you put -2 into the input of the function, all of a sudden you get confused. Do I output 4 or do I output 6? So you don't know if you output 4 or you output 6. And because there's this confusion, this is not a function. You have a member of the domain that maps to multiple members of the range. So this right over here is not a function. Not